let us list the effects. First, I played the Nobel Prize card once with my university to get the ability to park right by the front door. Second, I received constant requests for an endorsement, a contribution to a proceedings and the like. Really, many of them so annoying because they are, for example, in sewage disposal or health or electronics, things with which I'm absolutely not familiar. They are clearly just going after Nobel laureates in hopes of snagging one.
Jim Peebles is the Albert Einstein Emeritus Professor of Science at the Princeton University, and he's widely regarded as the founding architect of modern cosmology. He predicted the cosmic microwave background radiation, and he's made major contributions to Big Bang theory, introducing dark matter and dark energy, and to primordial nucleosynthesis. And he's a leading pioneer in the theory of cosmic structure formation. In looking up his biography, I found he had received so many awards and honors for his work that I could not begin to list them all. In 1982, he was appointed Fellow of the Royal Society, and in 2019, he won the Nobel Prize for Physics. His career spans over 5 decades at Princeton University, during which he has laid the foundations for almost all of modern cosmology. So, Professor Peebles, thank you very much indeed for joining me today.
My pleasure.
Tell me.
Small correction. I didn't predict the thermal radiation. That was, just for the history record, yeah. George Gamow had predicted it 20 years earlier, but it was forgotten. My thesis advisor, I was then a postdoc working with Bob Dickey's group at Princeton.
Yeah.
He suggested there might be this radiation. He told 2 of his young people in his group, go build a radiometer to look for this radiation, if it's there. He was too polite to mention that it's a Dickey radiometer, which he had invented during the Second World War. And he told me in a casual remark, why don't you think about the consequences? I did. And both the experimental and theoretical sides prospered.
And ever since that time, the theory of the cosmic microwave background has played an important part in the Big Bang theory.
Essential.
Yeah. And in fact, you laid the groundwork for the Big Bang. And what were the key moments, would you say, in your discovery and your career, which you would pick out as being the moments of enlightenment or things which suddenly came to you as this now explains the universe?
I'm reminded of the question, which of your children do you favor most? Impossible. But yes, there were moments. That it was understood clearly by all of us that if this is thermal radiation left over from the early stages of expansion of the universe, then its intensity, the intensity of the radiation at each wavelength, should be described by one number, the temperature, then the form of the spectrum is fixed. Of course, measuring the spectrum was a difficult art that required learning. There was a time in the 1960s and 1970s. In fact, there were a series of measurements that seemed to disagree with a strictly thermal spectrum. That disturbed me a lot because, of course, if the spectrum were from the early universe, but had been seriously disturbed by violent events after the expansion of the universe had gone on for some time, then we would be looking at a very complicated process by which violent events had disturbed the spectrum. That sounded too messy to me, and I didn't want to think about it. So for quite some time, I just didn't think about this thermal radiation. I backed off. But then, and you know, I don't remember now, late 70s, two groups managed to fly either a rocket or a satellite for precision measurements of this spectrum. It took both groups more than 15 years to get the answer. In one of these coincidences that happened, they had the answer within a few months of each other. They both told the story, no, the spectrum is wonderfully close to thermal, what you would expect if the universe had more peacefully evolved with this radiation. I might just remark what always bothers me about prizes that you mentioned. One group the leaders for one group received 2 Nobel Prizes. Let me put it better. One group, the scientific leader, John Mather, received the Nobel Prize for confirmation of this spectrum, richly deserved. He was not much more than a postdoc with a thin publication record. If he had gone through all the effort of getting this satellite launched and if it had exploded, he would be left with the deep respect of the few people who knew what he had done and little else. I don't think I could have stood sitting there watching them light the fuse. But it worked, it launched, it was wonderfully successful. He received the Nobel Prize, just perfect. But the other group in Canada on the West Coast, led by Herb Gush, equally well deserved that prize, but nobody noticed.
Well,
prizes and awards tend to be capricious.
No. Can I ask you, how does winning the Nobel Prize change a person's life?
You are an example. I wonder if you would have called me at this point if I had not won the Nobel Prize.
Oh, I've run a number of people who haven't won Nobel Prizes.
I can accept that. The one change, well, let us list the effects. First, I played the Nobel Prize card once with my university to get the ability to park right by the front door. Second, I received constant requests for an endorsement, a contribution to a proceedings and the like. Really, many of them so annoying because they are, for example, in sewage disposal or health or electronics, things with which I'm absolutely not familiar. They are clearly just going after Nobel laureates in hopes of snagging one. It's quite stupid. So I get a lot of requests. Most of them I simply ignore. I occasionally write to complain.
Oh.
I occasionally agree to do something. And as I said, I agreed to do something with you because you mentioned that you'd known David Bohm, who I find a very interesting figure.
Did you ever meet Bohm?
No. I arrived at Princeton in 1958. He was already gone.
Yeah, gone in 50.
He was remembered, and with unease, because, as you remark, he was driven out by the Red Scare in the United States. The fear that somehow communism is an evil organization.
And
led by Joseph McCarthy.
yes.
So we went through a traumatic period then, and of course, in my humble opinion, we're going through here in the US another traumatic experience.
You must have met many famous physicists, I suppose, during your long career at Princeton. Do any
Yes.
other ones stand out in your opinion as remarkable?
Well, I would slightly redirect that question to the fact that when I started working on this notion of an expanding universe, on the advice of my former thesis advisor, Bob Dickey, I was very reluctant to go ahead with it because the empirical support was so very meager. But I could find it. I thought I'd write a paper or two and then go on to do something meaningful. But each paper led to another, and my career was set. At the time, there were very few people doing anything interesting in this subject. So in a few years, I got to meet almost all the people doing something meaningful in this subject outside the Soviet Union. The one person I met only very much later was Yakov Zeldovich in the Soviet Union, who was doing very productive work. But for the rest, I knew all the major figures, and there were only a handful. Willie Fowler, Fred Hoyle, and others.
I was going to ask you about Fred Hoyle because quite in distinction to Fred Hoyle, he took the steady state view, didn't he, of the universe? And you've taken the exact opposite view, the Big Bang view.
Yes.
Your view seems to have been proved correct. Did you have any discussions with Fred Hoyle about this particular issue? And did he come round in the end?
You know, he did not. Fred Hoyle was a great scientist who I respect, but he just could not let go somehow toward the end of his career. It was a shame. We did have discussions, and during that time, the evidence for the hot Big Bang was still pretty meager. And so he had a scientific case that was valid for looking at this alternative to an expanding universe. And I remember his one statement: the scales of time and length in cosmology are so vast that there is no way that the subject can be empirically established. It must instead be discovered by philosophy. At the time, he had a valid point, but he failed to recognize that the empirical basis was being discovered and that the discoveries increased the such richness that we soon had a very persuasive case that yes, the universe is not forever, that it had to have been evolving from a dense state. Those tests of the theory have continued. By now, we have a pretty tight matrix of evidence that sure looks like the relativistic expanding universe is a very good approximation to nature.
Well, the cosmic microwave background radiation is a very powerful piece of evidence for.
Oh, it certainly is.
And I just wonder, what did Hoyle make of that? I mean, how would you explain that in any?
You recall he had the quasi-steady state cosmology, in which there were intervals of expansion, contraction, expansion, and contraction.
Wow.
with a general trend that looked like the steady state. I don't remember the details. He had the quasi-steady state theory. It was not at all ever promising to me, even because I'm very much influenced by the evidence. It just never seemed a natural way to fit the evidence.
No.
So he, I think, died an unhappy man. I think a tragedy because he was such a good scientist.
But, and he wrote books too. He wrote novels.
He wrote excellent books, persuasive books.
Well, one thing about the Big Bang theory, though, is that on its own, it runs into problems, doesn't it? The idea that the speed of the expansion of the universe didn't seem to match the amount of matter which was available to calculate the speed of it and how it would be slowing down or such like. So you introduced some new concepts. Can you tell us about that?
Well, the two concepts I think were most important was first dark matter, the notion that there is not only the sort of matter of which you and I are made, but another kind of matter that has come to be known as dark matter, a fair name because it's dark. It doesn't interact with radiation. It doesn't interact with the material of which you and I are made. I introduced that as a fix for the theory of the expanding universe, required to account for the fact, the observation, that the distribution of matter in galaxies is far more clumpy than the distribution of this thermal radiation. You wonder, how could that be? Because you consider that in the early universe, the temperature was very high. That high temperature would have caused the radiation to strip electrons from atoms, and those free electrons would scatter off the ions and off the radiation and produce a good approximation to a fluid in which matter and radiation would move together. How in the world can structures start to form out of the matter before the radiation is released, when finally it could escape the electrons? It was a deep puzzle, a crisis. So I proposed we have another form of matter. This was strictly ad hoc, a form of matter that doesn't interact with radiation, so it can start to cluster to form galaxies and clusters of galaxies. Well, the ordinary baryonic matter you and I are made of is still locked down with the radiation. That was an arbitrary hypothesis to save the phenomenon.
Can I ask, why didn't you reach out for ordinary matter here instead of dark matter? Because what comes to my mind, I mean, I've done physics as a training, but what comes to my mind immediately is if all the electrons are stripped off all of the atoms, you're left with protons.
Yes.
If you have enough protons with no electrons around them at all, just protons suffusing the universe, they wouldn't interact with radiation, would they?
Well, they would very seriously interact with each other. You need those electrons to keep the fluid neutral, or else it is a violently unstable situation.
Right. But neutrons,
protons repelling each other. And of course, we really need those electrons.
Okay.
We need them. So that wasn't easy. Another postulate that I did explore a lot was that you said, of course, an interesting point. Where did the material come from that made the universe that started expanding? There's an answer for that. If the universe started out very hot, then thermal processes would have created baryons and antibaryons, protons and antiprotons. And Bob's your uncle, we have them now. The problem with that, of course, is that by known physics, you make as many protons as antiprotons, electrons and anti-electrons. They combine and you're left with only radiation. There's a deep problem for particle physicists to explain why we were left with enough matter to make us. Something is a little wrong with our theory. That's not totally disconcerting. You know, all of our theories are incomplete.
Yeah.
But it required that leap of faith. Somehow there were more protons than antiprotons create. The creation is not the problem, only the serious need for an imbalance of matter over antimatter. So then, where are we left? We need creation. And although we understand the basic physics, the details are just not understood. Why more matter than antimatter? The conventional thought is that you make as much, that since the radiation would have to be very smoothly distributed because it resists gravity, you would imagine that the matter you create is evenly distributed. But you don't know that. And so you consider the possibility maybe the protons were created in a bunch here and there, along with the antimatter that then went away. But suppose there was a primeval clumpy distribution of matter. You can work through that. and see that it doesn't work very well.
Right.
And so we're left
You
with this.
haven't got a set of galaxies on one side of the universe which are made of antimatter, and another set of galaxies on this side of the universe which are made of matter.
Oh, well,
That
we
won't
can't
work.
check. That's difficult to check. But
Hmm.
the evidence is that that is the case, that all the matter is antimatter. The best evidence comes from high energy cosmic rays that are moving, particles that are moving, mostly protons, but also alpha particles that are moving so rapidly they can't have been contained by the magnetic field in our galaxy. So they likely came from other galaxies. And if the other galaxies were antimatter, you might be able to detect it, that you're receiving antiprotons, anti-alpha particles. Very little evidence of that. And so it does seem that the galaxies at a considerable distance are all matter.
Hmm.
But to get back to the point, oh yes, I made the point. Maybe the baryons were inhomogeneously distributed at first, doesn't work well. So the easy solution was assume there's lots of antimatter, lots of dark matter. We in physics, you know, we like to use the just so stories, how the leopard got its spots, Rudyard Kipling.
Yeah.
People are inventive. Give them a phenomenon, they'll invent an explanation. Give a very clever, very inventive theoretical physicist a phenomenon, they might come up with an explanation that is just the just so story. You need to test it by observations of its predictions. To begin with, dark matter was a just so story. It reduced the credibility of the hot Big Bang relativistic theory because I'd done something ad hoc. Let there be dark matter. But of course, even though the dark matter hasn't yet been detected, it has fit a lot of tests. I think there's very little doubt it's there. There's a very big question, what in the world is it? How does it fit with all the other matter we know so well and understand so well? But that's another story.
Right.
You mentioned the other important element, the cosmological constant.
Yeah.
You remember that 1915, Einstein had invented a new theory of gravity.
Yeah.
Very poorly tested at the time, but accepted by many for its elegance. It was at that time a just so story because it wasn't tested. Einstein had three classical tests, but one was the anomalous motion of the orbit of the planet Mercury.
Yeah.
But he knew already 10 years before he found his theory that that motion is anomalous. And he thought if he could find a new theory of gravity, it might account for that anomaly.
Yeah.
That means it wasn't a prediction, it was rather a goal. Historians will say it's unfair to say that Einstein just invented his relativity theory to explain the motion of Mercury, but it's not entirely wrong either. The second classical prediction was the redshift, gravitational redshift. Impossible to test on the sun because motions of the plasma on the surface of the sun gave redshifts and blue shifts that totally messed up the business. The one test of the three classical tests that was pretty sound is the deflection of light passing near the sun by the mass of the sun. By the time 1915, well, no, I'm sorry, by the 1930s, that measurement had been repeated many times. It's a difficult measurement, really
I think
massive.
Eddington did the first one, didn't he?
The first one was widely accepted, but I don't think with caution it would have been accepted.
Yes, I think it was fudged a little bit, but
the measurement was repeated many times. And so people accepted, yes, there is the deflection of light by the sun as predicted, and maybe 20 or 30%. But that's an awfully thin awfully thin evidence to accept such a grand theory. Since then, modern technology has enabled many tests of general relativity that it passes. It's quite an amazingly successful theory, and quite amazing that Einstein came up with it more or less out of whole cloth.
Hmm.
Just astounding.
It was Einstein, of course, who first introduced the cosmological constant into his
Right,
equations, which he described, I think, later as the greatest blunder of his life.
right. And who knows whether Einstein, who was not a self-depreciating person, really meant that. Uh, let's recall Einstein had built his theory in 1915. Uh, he had philosophical reasons for thinking that a sensible universe is the same everywhere, which is what is observed if you average out small fluctuations like you and me and planets and stars and galaxies. In the average, the universe is just what Einstein imagined. Another spectacular stroke of intuition that many will say, I would agree, he said a bad example. You shouldn't make wild, you should be guided by the evidence,
Hmm.
but well, if you're Einstein, you can get away with it. Anyway, he discovered that his new theory with a uniform universe is quite untenable because the universe would either expand or contract.
Hmm.
He introduced the cosmological constant, which serves as a repulsion to balance gravity to get a stable universe. And
He
of course,
wanted
everyone
a
knows the
steady state.
universe is forever.
Yeah, he wanted a steady state situation, didn't he?
Yeah, he did. And I don't know, he certainly wouldn't have put it in those terms, but
Yeah.
uh, isn't it obvious that the universe is forever? Well, of course it isn't, but that was certainly a very natural thought. He
Hmm.
introduced his cosmological constant for the purpose of stabilizing the universe. He didn't pause to consider that this stability is unstable. The slightest disturbance will cause the universe to collapse or expand, or more likely, some parts will expand, others contract, and it'll be a total mess, not at all like what we observe. So Einstein soon decided that this cosmological constant is an ugly appendix that should be abandoned. Now, whether that was a great, if he had accepted the notion that the universe would either expand or contract, then he could have claimed to have predicted the general expansion of the universe. Did he really have that thought? As I understand it, the notion of blunder came from George Gamow, who was the most deeply intuitive physicist I've ever encountered. The guy was a genius, but a genius of a sort who really didn't care about details.
Hmm.
Lots of examples, but such a detail as whether Einstein ever really said that would not have bothered Gamow. A
Yeah.
genius, but not of that sort. There, we are very fortunate that people are all different because there are so many tasks to be done in the world. And Gamow made a wonderful contribution to science and society, but he had his ways. So
I have an appreciation of Gamma because it was really through him that I became a physicist, I would say, and
uh,
because I read his children's book. I called it children's book, Mr. Tompkins,
yes,
and that was a fantastic book. I read it was about 13 or 14, and it sort of opened my eyes to a whole new world. And I thought that's really great. Relativity was part of it, and then there was quantum mechanics. And I thought, gosh, this is something I never heard of at school, and it's quite amazing. So that sort of set me on my own journey, I suppose, with Gamma. Never met him, of course, but
read those books too.
yeah. Well, I mean,
But you know, my experience is different from yours. Somehow, I'm a kind of scatterbrained person. I, I reflect back that I was hungering for physics from an early age. but I didn't realize there was such a subject as physics. I went to a very small high school where I paid little attention to anything. I was just a dreamy kid, not really reflecting on what I was doing or where I was going. I didn't realize, but I went to the university, and only there did I realize that there is a subject called physics and that I love it. It hadn't occurred to me earlier.
No.
Just a scatterbrained kid, but we came out all right.
You know, I think that David Bohm, I heard that he had the same kind of experience, that he didn't know much about subjects until someone gave him a book on astronomy. He was so taken up with this book on astronomy that it changed his whole outlook on what he wanted to do with his life. I think his father wanted him to be a businessman, but he decided no, physics was more his area. So he, again, influenced by books and things of that nature.
My parents didn't push me either way, and
No.
I'm grateful for that because somehow I think my loose upbringing gave me the freedom to think, which I still enjoy. A
It's
walk
the
in the
freedom to
park.
think, which often we don't have today in universities, it seems to me. Everything is often chasing grants, and grants are determined by external agencies which tell you what to think about.
And I'm so distressed to see students walking around our beautiful campus with a cell phone to their ear or their mouth.
Yeah. Because it just takes away your concentration time and your ability to spend time looking at, say, real things. Yeah.
And thinking new thoughts.
Yeah.
Well, at our age, we are bound to complain. Mark my words. Anyway, we're still talking about Einstein's cosmological constant. It was when I started looking into this subject of the expanding universe, the cosmological constant was considered a silly thing, not worth considering. That was certainly reinforced by the particle theorists because in quantum physics, there is a vacuum energy density, which is expected to be spectacularly large, but it doesn't matter because you always measure energy differences. I took a lot of quantum mechanics courses. I was constantly reassured that extra energy doesn't matter. We look at energy differences. But of course, general relativity theory that now well accounts for the expanding universe looks at the energy density. We have the cosmological constant required. It is in effect an energy density, but it is ridiculously small compared to what quantum physics predicts. So in the 1990s, it was well known, the particle theorists said, well, the only possibility is that this quantum vacuum energy density happens to be zero because of a symmetry to be discovered that requires that. Zero is the only possibility. In the 90s, I was arguing that we could solve some problems in cosmology if we brought back lambda. I remember being carefully instructed by quite a few particle theorists on why my idea was ridiculous. They were polite, but Jim, you got to understand. The problem was, shall we get into the problem? Why not?
Yeah.
There was the notion at the time that the curvature of space, space is pretty flat for us, but in fact, in a homogeneous universe, space can curve like a balloon or like a saddle.
Yeah.
And it was pretty clearly demonstrated that the curved universe, curved space is not really possible. Let's not get into the reasons why. It was a fixed belief. One says natural scientists should not have fixed beliefs. We have all kinds of fixed beliefs. We struggle with them. We struggle with the evidence and we make progress, but slowly. So in Einstein's theory, a universe that has flat spaces requires a certain mass density. You can calculate it. The theory is unambiguous. I was looking in, I spent a lot of time looking into the mass density universe. And the evidence I had accumulated is that the mass density is well below what is required if the universe is described by Einstein's theory and its space sections are flat. I enjoyed going to many conferences at that time in which people talked about the flat universe. And I would present a talk saying, but the evidence is wrong. It says that that's wrong. And it's an interesting experience because I could go to a conference, give this talk, clearly make my point. Everyone would absorb it. But by the time of the next conference, they'd forgotten. It's just too unpleasant to think about lambda.
Did you find the space was curved positively like a balloon or negatively like a saddle?
It would be negatively like a saddle because of the low mass density.
Right.
If there were no lambda, no cosmological constant. I remember the remark of now a very senior and well-respected scientist, then a beginning postdoc, who complained about my insisting on arguing for the presence of Einstein's cosmological constant called lambda. He said, "You're only doing that to annoy us." And I was able to pull from Lewis Carroll, I only know because I know it teases. And indeed, I did take pleasure in annoying my colleagues by presenting this unwanted evidence. Anyway, the evidence, the evidence for the cosmological constant grew. We may not need to discuss that now. Now it's clearly established. We need that cosmological constant. We are left with a really deep problem. The mass density you expect from quantum physics and the mass density you expect from cosmology are wildly different. That is a fascinating problem. Both theories are well tested, but we have these days two theories, both well tested and successful, but inconsistent.
Yeah.
A small scale theory, quantum physics, that goes wonderfully powerful. All kinds of tests, deeply, deeply productive, deeply well tested, and just a beautiful theory. We have a large scale theory, general relativity, now very well tested, securely tested by tests of general relativity and tests of the theory of the expanding universe. Two well-established theories, but they don't meet. Isn't that remarkable?
What's your view of that? Do you feel that there is some grand unified theory which, once we discover it, will unite those two separate arms together? Or do you think that this is something which will remain forever unknown because two things may not necessarily have to be joined together?
It is the first. I will not use the word belief. My intuition, my hope, expectation is that they will be reunited. But I have to be honest, it's possible that they won't be united. I am pleased to recall Snow, C.P. Snow, on the two cultures. I see an analog. In physics, we have two physics that don't get along. Isn't that interesting?
Well, I mean, C.P. Snow was talking about art on the one hand and science on the other, or humanities on the one side and science on the other. But within physics itself, we have at least two, if not more than two areas.
Oh, well, if you start to think about what is the physical meaning of a living object, you can put that in a separate category, but I wouldn't do it.
Schrödinger tried to do it.
Oh, yes, and that's big science now.
Mm.
If you're going to make real progress in curing all the illnesses of people, and there is enormous demand for it, you are going to have to understand better what it means to be a living object, a, a
And
small
do we have a
world.
definition of that, do you think? Or do you?
Right. Can you define what it means to be alive, living?
It's very difficult because you have things in the middle, don't you, like viruses, which they replicate,
Yes. Yes.
and yet you may not say that they're living.
Right. I don't think they're malicious when they go after us.
No, I don't think so either. They just happen to work against.
So being malicious is not a good definition, though, of life.
I mean, there are those who use entropy as a definition, that everything is working down except that which is full of life works the opposite direction, and entropy is decreasing.
Well, the evolution of the expanding universe violates that.
Does
We're
it?
growing more complex,
That's interesting.
large scale structure.
That would make the universe a living thing by that definition.
So we need a better definition.
Maybe we do. Yeah.
I think
Trouble
we
is,
don't have one.
all definitions are arbitrary to some extent, aren't they?
Of
They're
course, yes,
categorizations which we create ourselves.
yes, and they can be traps.
Yeah. So, I mean, looking at we're talking about mysteries here, but looking at today's cutting edge research, cosmology or other areas too, which current mysteries most interest you at the moment, and why?
Well, it's not surprising, perhaps, since I grew up with the development of our large scale theory, that I'm still interested in it. This I mentioned through my career, I was in the wonderfully fortunate situation of being more or less alone to develop the subject.
You can't do that these days, though, can you?
That's right. Although, in fact, because in the large scale theory, you can. There are now two branches of research. One, large scale projects and meant to do better what has already been done. That requires large teams to develop a rocket, a satellite, say, or a very elaborate laboratory experiment as an accelerator.
Well, things like the James Webb Telescope have made massive impact, haven't
Yes, yes, a spectacular development. And again, John Mather, I mentioned earlier, he was chief scientist for the JWST. Again, he sat there in the stands watching the fuse lit and that thing going up. And after it reached orbit around the Lagrange point, they opened it up and it worked. With the Space Telescope, the prescription for the lenses was miscalculated. And so deep embarrassment to NASA, but they could send up, that was in a relatively low Earth orbit, they could send up astronauts to fix it, to give it a prescription. Now it's working to spec, marvelous. You can't get up to the JWST, too far away.
Yeah.
It had to work, and it did. Anyway, why are we taking that? Is a massive project that is producing great results.
So what can someone do on their own?
I am on my own investigating what I would say are interesting highlights, sidelights. I think it's fair to say that in the rush to discover and establish the standard theory of the expanding universe, there had to have been tendencies to come across annoying little results that could be put aside because they didn't seem to be relevant. Put aside for later consideration, then of course you forget about them. I'm, I have an example. I'm betting there are more. These are things that, for preliminary exploration, require only one person and maybe some papers and pencils and maybe a computer of modest size, all of which I have. And then, of course, I have a lot of time because I'm retired. It has long been known that the galaxies near us tend to be close to a plane that passes close to us. It was discovered by the astronomer Gerard de Vaucouleurs in the 1950s already. And it was perhaps in the nature of unwelcome evidence. It was ignored for years. But in the 1990s, other astronomers, in particular, with age, memory goes.
Yeah.
People began to notice that this plane extends rather far out. And so there was there are occasional papers noting that galaxies pretty far away seem to like to be on this plane or close to it.
Yeah.
But it never went anywhere. So I've taken an interest in this phenomenon. I have argued.
With an explanation?
Well, no. Yeah. First, the phenomenon I think is now pretty well established, though not widely appreciated. And I am just now running another test. But anyway, what could have caused this? One possibility are cosmic strings. They are to be distinguished from the superstrings of string theory. Cosmic strings are simply lines of energy and mass of a field that is sort of wrapped up in a tube. You can make theories in which that would happen. These tubes running through space will tend to attract matter and leave in its wake a little sheet of extra mass density.
Wow.
It is very natural in particle theory to imagine these fields that make these tubes exist. No evidence they do exist, but it's not unnatural. It's natural to assume they do exist. Whether they would be produced in the early universe is not known. But if they did exist and were produced, they could produce sheets of extra mass that might be expected to provide the extra mass could provide sites for galaxies to more readily form.
Right.
Which would be fun, which would be fascinating.
Well, it seems
so.
Yeah.
I am looking into this notion, not about the cosmic strings, but simply about the phenomenon, is still in very early stages. So I, without much fear of competition, can work through tests, the little tests that you would do before you made a big test.
Talking about competition, if you do you have any advice for younger scientists who are just starting off on their careers and hoping to emulate your success in some way? I mean, you've had an extraordinary career spanning, decades. You're now, if I may say, in your 90th year, and you must have a lot of experience in looking back. What advice would you give to young scientists? What might they take up?
First, remember that history might not your experience inevitably will be different from mine because situations have changed.
Yeah.
I did not have to worry too much about being considered a nut because I was at a powerful institution with a very powerful advisor. I could throw out ideas and They didn't seem to tarnish me. But that's a uniquely favorable situation. I advise you, as students looking to go into physics, looking to start research in physics, to be cautious about getting yourself associated with too many projects that are normally considered foolish. A project can be considered foolish, but very, very, very profitable, but you don't know that. And so keep a limit on the number of such projects you engage in so that you're not left with the label of a nut. This sounds cynical, but there it is.
No, I've heard that advice from other quarters too. I was listening to John
Uh-huh.
Searle, the philosopher of mind, and he said, whatever you do when you're starting out, don't study consciousness until you've got tenure, which is how he
Yes. And that also sounds cynical, but true.
yeah.
Once you have tenure, you can no. I depreciate scientists with tenure who involve who involve their research students in their research. They should be very thoughtful about what that might do to the student's career. It is very good for a senior physicist or senior person to indulge in speculative activity. They might come up with something interesting. In fact, if you don't indulge in speculation, you're going to be far less likely to come up with something interesting.
Yes.
But be sure that your students don't get labeled with these highly speculative ideas.
I remember when I was trying to choose a PhD, UCL, which is the university I was at, were very kind to give me a roaming grant to choose any PhD area I liked. And I went and looked at lots of different areas, and one I did look at was cosmology. There was a professor there called Michael Seaton, who
Yes, I know the name.
yeah, and he was producing computer models of the interior of stars. And I
Mm.
recall that if you wanted to do a PhD with Michael Seaton, he had these great drawers of Fortran cards, you know, the old punch cards.
I
And if
remember
you
them
were going
well.
to be a PhD student, all you would be contributing would be one small bunch of additional cards to fit into his model, which would which would fit into one of his drawers somewhere. And I thought to myself, that's not the kind of small thing which I was interested in anyway. I wanted something bigger, which is why I moved next door to where Bohm was, because they were looking at bigger questions. But would you
Yeah.
encourage young people to look at big questions today, or would you encourage them to stay in a small little area and do a small thing?
But I would encourage them to do both.
Oh,
Um,
fair enough.
uh, another cynical expression I like is keep your day job,
Yeah.
uh, but don't confine yourself to it. Think more broadly.
If I
But
we're coming roughly to the end of our time, but if could I ask you? I mean, as someone who studied the universe's structure and history on a grand scale, do you ever ponder the why behind it all, or do you just strictly stick to the how?
the why is fascinating. But the same question would arise if I were studying small scale physics.
Yeah.
They're the same. It's the same question. Um, and since I can see no way of testing that issue in any way, I I stand back.
Right.
Um, maybe I should tell you that as a youth, I in Canada was occasionally persuaded to accompany my mother to services in the Anglican Church of Canada.
Mm.
I hated it. I just couldn't wait to get out of there. I just couldn't know what was going on. I didn't want to know. I now remember, and on occasion when I do attend services, some of the beauty of it. but I didn't appreciate it then. And I have never appreciated truly the beauty of religion. You could be inclined to say, well, I have an answer, but I will never consider it, because I love the fact that our ideas can be challenged by evidence, experimental, observational.
That really is the heart of science, as I can see it. And the moment we stop allowing ideas to be challenged, then we stop making progress and discoveries and getting even closer to the truth. But can I put my question to you another way around then, without the religious connotations? I mean, has your study of the universe at large informed you of any degree about what it means to be human and how humans should live, or the quality of life itself?
Do you know, I am inclined to think in another direction, that humans are not all that special. Do you know that in the United States, the phenomenon of monarch butterflies, who spend their summers in the northern parts of the continent and their winters in Mexico, to the south of the continent, these butterflies migrate. And what's more spectacular, a single butterfly doesn't make the whole trip. In the southern tip of the state of New Jersey, there is a gap, and then the state of Delaware on the other side of the Delaware River. At that southern point of New Jersey, there is a forest with trees. Then on one occasion, we came across one covered with monarch butterflies. I asked the ranger, "What are they doing?" And he said, "They're waiting for the wind to change to blow them across to Delaware." You know, I'm thinking one of my brain cells is worth nothing, and one butterfly is worth even nothing. But a lot of butterflies can do something intelligent. They purposefully stop until the wind is right.
Yeah. Collectively.
I purposely stop talking about such things when I know it's appropriate. The collective activity of things is encapsulated in my picture of the brain. And I'm so deeply impressed with nature and what it can do. I'm impressed by what people can do, but so can plants. Many things to me. It's a wonderful place, but I don't think we should get too proud.
I have one last question for you, if I may, Professor, and that is, when you look back on your massively successful career, what are you most proud of, and what do you most regret?
I regret nothing.
Well, that's good. That's good to be able to stand at the end of one's career there and say, "I regret nothing." That's very good.
Right. I could have been, no. I can't, I was so lucky that I never had cause to regret. I don't like to boast, but there it is.
That's good. And the one thing you're most proud of?
My children.
Yeah. These kind of things and human relationships outweigh most of our professional, if not all of our professional lives, don't they? But that's a good place to end on, I would think.
Well, I'll make one final remark. I value my wife too, but she's sometimes annoyed with me for spending so much time here at the university.
Well, you can be forgiven that, I'm sure. Professor Peebles, thank you ever so much for a fascinating conversation today and for your time. Thank you.
I enjoyed it.
Ah, Jim. May I call you Jim?
Of course.
That's very kind of you.
I have to discover how to turn down the sound a bit. Oh, here we go.
I'm too loud for you. Sorry.
No, the machine. Well, okay. So here we are.
I can hear you very
Have
well.
you can hear me?
I can hear you, yes,
Oh,
and you can
good.
hear me.
So we're
Great.
all set.
We're set to go. Can I just begin by saying thank you very much indeed for your time, because I very much appreciate that. You must have lots of things attracting your attention in different directions, and I'm thankful you're able to make some time for me today. That's very kind of you.
Well, it was your mention of David Bohm.
Ah, David Bohm. Yes, well, I was only a PhD student at the time when I knew David Bohm. We're talking about 1977, 1978, 1979. I got my
Well, he
PhD.
had left Princeton.
Yeah, and he was very kind and generous man, and
Mhm.
he gave a kind of a weekly session to all the postgraduate students. Every once a week in his room, we would all gather. We so many of us, probably about 8 or 9 PhD students. We'd all sit around on the floor mostly, and we would sit at the great man's feet, quite literally, and listen to what he had to say. Nothing was prepared. He just answered questions, and we brought all kinds of questions to him. And he spoke very gently, but with great fervor. He was quite a shy man, I would say. But when he got into talking, he kind of his spirit seemed to glow, and he would begin to be very animated. He had unusual mannerisms, which I still recall, the way he flexed his hands quite a lot, and the way he often took out change from his pocket and played with coins. That he did that incessantly. Um, but there was no question which was too out of the ordinary for him. He was quite happy to answer
Mhm.
whatever we had. I remember I didn't please him too well when I said I was a great devotee at the time reading Karl Popper. I hadn't realized he'd spent some time with Karl Popper, but he kind of dismissed his ideas
Popper.
quite,
Yeah,
quite, quite
right, right.
fervently. But of course, he spent quite a lot of time at Princeton in the early 50s
Mhm.
until he was dismissed, really, by
I'm afraid that was right.
yeah. Yeah, it's a difficult time for America, I think, as a
The
whole.
Red Scare, yes, a difficult time for America. Some consolation, perhaps, or some comfort for what we're going through now.
Yeah, yeah. Anyway, Jim, if I may,
Hmm.
we could make a start. And what I normally do is I just do a kind of a 20-second introduction to yourself, and then move into the first set of questions. We'll see how we get on. Is that all right?
That's fine.
Thank you. So let me begin. Oh, by the way, if I say something which is incorrect, then please do stop me in my introduction, and I'll
I'll do
just
that.
do it properly. Thank you. What I plan to do is I will top and tail this interview. I don't edit anything out from the middle. I just keep just take off the beginning and the end where it properly ends, and then I hope to put it out on YouTube as soon as I possibly can, maybe tomorrow if that's possible. One of the
Um,
advantages of I've just retired this year, so I get more time to do that. But thank
Retirement
you
is
ever so much.
wonderful, but do not hesitate to take out sections where I might hum and haw or maybe confuse people. Feel free to do it, and
I will
I
try
want
not
more
to,
control.
but
It's
thank you.
yours now.
Thank you ever so much. I'll send you a link to it as soon as it's up and running in case you want to see it or pass it on.
I'll probably not.
It's been a great time talking to you, and I feel very privileged. So thank you very much indeed.
I enjoyed it. Take
Thank you.
care.
Bye.
Bye. Leave. Ah.